So with the remaining hour we have left, I was going to go into the more advanced features of Python, more exciting things. So there's a couple of so to be sure, these aren't necessarily advanced features of Python necessarily, but they are advanced features of programming languages. The first of which is I'll briefly introduce recursion because it's fairly interesting, and since you may not be taking another programming class, it's useful for you to know what recursion is. Okay, so what is recursion? So let's go ahead and show you. So here is, so basically I'm going to introduce it. I'm going to show you a mathematical definition you should hopefully know by now. Do you know what the factorial operation is? So if I were to say 5 factorial, right? 5 times 4 times 3 times 2 times 1, right? The factorial operation is basically when you've got a number followed by an exclamation point, that is equal to 5 times 4 times 3 times 2 times 1, okay? So in other words, if we generalize this out, n factorial is equal to n times n minus 1 times n minus 2, and yeah, I should add parentheses to be good about that for order of operation's sake, because otherwise it's going to be a real big mess, dot 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 times 3 times 2 times 1, right? We also have this weird odd definition here that 0 factorial is equal to 1, oddly enough. Don't ask me why. I'm not the math professor. I'm just simply using a mathematical definition because this is the classical one of the classical examples for recursion. Okay. Now suppose recursion is one of the basically the elegant weapon inside in the programming arsenal. It is the tool for making your code nice and readable and powerful. Recursion allows you to basically, and it uses your greatest trait to your advantage once you've become comfortable with the phrasing of it, which is your laziness, which is that simply we are going to break down a problem into a smaller subproblem, which is the same problem, by the way, but it's a smaller version of the same problem. That may not make sense, but basically what we're doing is that we're taking a problem, breaking it down into a smaller version of the same problem. Okay? So let's just go ahead and see how this looks in a iterative function. Fact iter. So this is when we use, if we were to basically do it this, if we wanted to calculate factorial using an iterative method, right? Product is equal to 1, right? For I in range n, so if this is from, or rather 1 to n plus 1, so I have to do that thing, right? Product is equal to product times 1. So not 1, product is equal to product times I, right? And then that's it, return product. In other languages, it does get a bit messier. Print fact iter. Let's print fact iter 5. Save it, run it, and it gives me 120, which is 5. So now we have to actually confirm that's the correct answer. 5 times 4 is 20, right? Times 3 is 60, times 2 is 120, times 1 is 120. So it seems to be the right answer. Okay. Keep that in mind, that basically there might be easier ways to do that mentally. So keep that in mind. All right. So what does it mean to be recursive definition? To calculate recursively. To calculate it recursively means that we are going to call the same. We're going to write a function and it's going to call itself essentially. To be a recursive function, you need 3 things. The first is you need to have a base case. Basically, a version of this, a subproblem that is so simple that you can just automatically hand the answer back. The second is that you need to have a recursive case, which is that if it's not the base case, you have to be able to break the problem into a smaller part and then the third part is that you solve that smaller part recursively by calling the same problem. It's easier to see once you have an example. So first let's say we're calculating the factorial we're calculating n factorial. The first thing we do is consider the base case, which is also going to be our stopping point. So so this is the version of the problem that's so simple that we can just stop right there. So if n is equal to 0 or n is equal to 1, right? If we're calculating 0 factorial or 1 factorial, right? Then we know what the answer is automatically, right? What's 0 factorial or 1 factorial? It's 1. We're going to return 1. Okay? Makes sense? So, and the nice thing is that this lends itself to a mathematical definition, a mathematical formula pretty easily. So the other case is that what if we have a recursive case? Well, if we have a recursive case, we solve this problem recursively, which means that we are going to break this problem down into a smaller portion. So the question is how? So so that this last line makes sense, I'm going to put the comments up here. So let's look at 5 factorial. I had to compute that by doing 5 times 4 times 3 times 2 times 1, right? But actually, there's an interesting property about factorials, right? 5 factorial is equal to 5 times 4 times 3 times 2 times 1, right? And if I break this up a bit, I can do this as 5 times what? Any takers? 5 times what? What is 4 times 3 times 2? Not like what is the numerical definition, yeah, that's 24. What I'm saying is, like, can I rewrite 4 times 3 times 2?
4 factorial?
I could do 4 factorial, and that's exactly the key. 5 factorial is equal to 5 times 4 factorial. And if you think about it, 4 factorial is equal to 4 times 3 factorial, right? Let's look at that. 4 factorial is equal to 4 times 3 times 2 times 1, right? But 3 times 2 times 1, that's 3 factorial, right? Yeah. So this is what we're doing there. So n factorial. So basically, if we have a definition for so now we have a definition for n factorial that's actually very elegant to write here, right? N factorial is equal to n times n minus 1 factorial, okay? Right? The question is, though, with a comma here, if n is greater than 1, right? Otherwise, it's equal to 1 if n is equal to 1 or 0, right? So now what we'll do here is that we're going to return n times factorial of n minus 1. Now that seems a bit weird, but here's the idea here. This will constantly make progress towards the base case. So if I call, so let's see how this works. Fact of 5. If I print fact 5, just to prove that it works, that this black magic works, it gives me 120. Okay. Now, why would you want to do this? Well, because a lot of problems are way easier to express in terms of recursion, rather than not being able to express it in terms of recursion. You can take a mathematical example and blend it and turn it into recursive pretty easily. So this is a feature that I just wanted to show you. I have a whole lot more lectures. They're done in Java on recursion that, if you're interested in the subject, you should definitely check them out. They're under the 2168 lectures, and the Java shouldn't really give you some issues, but I go over these examples in depth. So why should you use recursion? Because, believe it or not, recursion is a bit slower because you're having method calls that you have to unwind. And the reason is because recursive functions generally are easier to read than their counterparts, than the iterative counterparts. So if I go over here for a second and write on the board though, right, how did this 5 factorial work? How did we get there? Well, we had 5 factorial. Sorry. We had 5 factorial, right? And that was, and what we did is that we did an if statement first. We asked ourselves, is this 1 or 0? No, it is not. So we have to return 4, so 5 factorial is equal to 5 times 4 factorial. Okay, so what is 4 factorial? Well, that's equal to 4 times 3 factorial. 3 factorial is equal to 3 times 2 factorial, right? These are just methods calling methods. 2 factorial is equal to 2 times 1 factorial. Okay, what is 1 factorial? We don't, that 1 factorial returns 1, so now we can return 2 times 1, which returns 2. Then we can do 2 times 3, which returns 6 for 3 factorial. We can then do 4 times 6 to return 24 for 4 factorial. And then we can do 5 times 24 to give us 120. So there's a lot of, so you can do recursion. It's a very powerful tool, being able to do that. But the keys to being able to do recursion successfully is that you have to have a place at which it stops, right? If it doesn't stop, you're going to get an infinite loop. Now, this isn't a unique feature to Python by any means. What is fairly unique to Python, though, as far as like other languages that you'd be exposed to in a college setting, is the fact that it treats functions like a first-class citizen. So this is what kind of the lecture is about. It's less about recursion, and more about what we can do with functions. This is all because you can do a lot of stuff with functions here. Okay, so let me go ahead and write a function over here, just in the interpreter. Okay, def add. Actually, let's just go with something easy and easier. Def double. Right? This is a function that will double something. Okay? It takes in a number x, right? And it will double x. So it will return x times 2. Okay? Right? Everybody okay with that? I just did a function over here. Double 4. Right? That's going to give me 8 back. No problems there. Now, what's interesting to note is that variables can hold anything in Python. Like, so for instance, right, if you type out just double by itself, the word double, right, I wrote a function called double, so it tells me its type is a function double, right? If I ask what type it is, well, I've actually never had to do this before. It just tells me it's a function. So this looks like, so if I had like an integer, if I asked for type like 1, it'll tell me it's an int. If I ask, so, and I can store integers and variables. So can I store a double? Sorry, can I store a function in a variable? And the answer is surprisingly yes. Double is equal to f. So f is equal to this function at this memory location, right? And if I type in double, I get the same thing out. They're the same function, right? Everybody see how that's how Python's saying they're the exact same function. They're at the same place. So if I call f of 4, right, that will double 4, right? So you can rename functions, and you can store functions in variables, which is really nice because a lot of times there's a common thing. What you want to do is that a lot of times you'll get a list of numbers, right? So let me create a list of numbers. Import, I guess, random. So let's remember how to use random. Random dot, let's see, random dot, rand int. And let's go ahead, and this will give me a number from 0 to 10, I believe. 0, right? Random.randint will give me a number between 0 and 10. I mean, random stuff happens. There was a 1 in 100 chance of that happening. That's odd. So this gives me the numbers 0 to 9. Okay. Got a lot of zeros there. That was pretty interesting. But, all right. So now let's go ahead and but basically, let's say I've got a list. I can say, here's another thing I can do. I can say, let's see. Let's go ahead and do so L is equal to an empty, L is equal to an empty list. L is our list. We're going to make an empty list. For blank in range 20. So we're going to do, we're going to do a for loop 20 times. L dot append the random number. So now L has a bunch of random numbers in it. I can sort them, but that's fine. So what's interesting is that basically, suppose I wanted to double everything in this list, right? Suppose I wanted to double everything in this list. That's not too hard. What I would do is something along the lines of, and I'm just going to create a list called L2, which is going to be my output, right? L2 is equal to a copy of L1, okay? So actually, I'm going to actually call this output, or yeah, let's call it L2. L2 is equal to a copy of L1 because I don't want to lose my original list, okay? L2, right? So for item in L2, well, actually, I need to enumerate it, right? Or actually, range. Yeah, for item in range length of L2, right? So that I can go through all the indices. So that would be item, that would be I. So for each index in this, L2 of I is equal to it's equal to what? L2 I, and we wanted to double it, so we can just use our double function to do that, right? Double L2 12 10 2 16 18 0 18 6 12 16 2 0 2, right? So it's doubled everything, right? Now, applying a function to every element in the list is actually a really, really, really common function. It's like, or rather, a really common operation that we want to do. So common that we have a special operator for it, and that's called map. So this is kind of cool over here. So map does two things. It takes in a function, and it takes in a list. And then it will apply every function, everything into that. So it will apply every operation to that list. So let's go back to L. And let's go ahead and give it double. So this will map double to list. This means that I'm going to apply the function double, right? Notice that I don't have parentheses there because I'm passing it as a variable. This will use the function double and pass it to every item in the, and do it on every item in L. So it gives me this map object, and if I want to turn it into a list, then I just throw this into a list, and that doubled everything in L. So you can use map to do that to every item in there, which is nice because say you wanted to double everything and find the sum, then suddenly we have one-line solutions for everything, such as sum map double L, and that gives me the sum of doubling every number in the list. So sum is a function that takes in all the numbers and gives you of a list and gives you a sum. So there's a lot of nice features you can do right there with that. So you can pass. So as another thing, you can also pass a function into a method as a parameter, right? So let's go ahead and write this def function fun, right? it's going to take in two variables. It's going to take in f and g and x, right? Where f is going to be a function, g is going to be a function, and x is going to be a number, right? And all it's going to do is that it's going to return f of x plus g of x, right? Which are essentially calling, which this is math essentially. It's saying we're going to call function f passing it x and call function g passing it x as well. So let's go ahead and define two functions such as function flip, which gives me an x, and if x is less than 0, return x times -1, else, actually no, all we have to do is that if we wanted just to add a negative sign, then all I have to do is just return x times -1, right? So this will flip the sign. Def, let's go ahead and do another one. Let's just do a simple one, cube, right? Which will take in x, and it will return x cubed, right? So if I print function, so if I do function fun, and I pass in flip and cube and 5, let's see what happens. Fun.py. Run it, and I get 120, right? So flip gives, so what happens there? Well, I had two variables. Oops. Yep, so what I did is that this gives me, so we passed in the flip function, so we passed in the flip function as f, the cube function as g, and then I asked to do f of x, so flip x. In other words, flip 5. So that gave me back -5. And then g of x, which was give me the x cubed. So that gives me 125. So 125 plus -5, that gave me 120. All right. So so that's kind of, so you can do those kind of things with expressions like that. With functions. So one other thing you can do with functions is, just like you can create string literals, there are such things as function literals as well. In other words, there's functions you can define basically in line. And that's by using lambda expressions. So for instance, what I can do is that I can do something along the lines of, let's say, let me just make this a bit easier to read. Print ans. So function fun, here I need to pass in two functions. I'm going to pass in lambda x colon x plus 1, lambda x to the 5th power. And what this has done is that this has created two functions basically without actually ever giving them a function definition. What this says is that this function will take in a variable x, and it will yield x plus 1. So if I gave this 5, it would give me 6. If I gave it 7, it would give me 8. This one says, if you give me an x, I'm going to give you x cubed. So now if I run this, let's see, it will give me 6 plus whatever 5 cubed is. Invalid syntax. What did I mess up on? Oh, one parenthesis too many. Okay. And that gave me 31, which, let's see, what is 5 to the 5th power? And then what was, then plus 6. So you can create functions basically out of thin air like that, which is pretty nice. All right, what other kind of features are there in Python? There are things like list comprehensions, which basically you can also create a list and populate it in line. Like, for instance, L is equal to, here's an example of a list comprehension. I'm not even going to bother saving it. X for X in range 0 to 100 by 5, and it gives me those. So now let's see, how does filter work? So there's another thing you can do in Python, which is using the filter operation. Filter, Python. And that basically allows you to give, if I pass a function in, it will weed things out. So let's go ahead and grab this list again, right? Which is the list of all of numbers up to 100 by 5s, right? So let's go with L is equal to this. So if I wanted to filter things, I can do filter lambda x, and lambda x mod 2 equals 0. So that's going to return true or false, right? That's going to return true if x is a it's going to return true if x is even, false if it's odd. I'm not sure. I mean, that kind of returns what it is. Right, so let's go ahead and do this. I mean, watch what happens here. So now let's throw this into a list. So everything that was even, everything that the filter returned true for remained, and if it was false, it was removed from the list. So it filtered out everything that wasn't in there. So it makes it very, very useful to do that. Let's see. I just can't remember if I can use it in together with list comprehensions as well. Let's see. Yes. So another way to do that, though, with list comprehensions is you can add an if statement into these list comprehensions. So x for x in range, so here's all the numbers in that are 5. If x mod 2 equals 0, and that will return basically, that'll only include x if x is a number. So these list comprehensions, by being able to add an if statement in there, they're fairly powerful. Unless? Does Python have an unless? I mean, it's an if over here, right? So the reason we have an if is because, I mean, else you're not going to include it, right? I mean, I do wonder, though. Invalid syntax can't include the else there. And which makes sense because you're filtering things into the list comprehension. All right. So those are kind of more advanced features in there. Your book does include there's also another key word you might see and you should use, which is the assert. So assert true won't do anything. Assert takes in a Boolean. All right. Let's see, does it work like that? Assert true. Assert takes in a Boolean. If you do assert true, nothing happens really. However, if I do an assert false, this immediately calls an error called an assertion error. And these are basically ways to create your own errors in your program. This should be true. Assert, maybe it needs to be an assert false I pressed enter instead of I pressed enter too soon. If you say you assert false, so you have an assert and then you have a boolean. So the way assert works is that you have an assert statement, the keyword assert, then you have a boolean statement, and then an optional string there. And that string will tell you what it will basically be the output for the error that you just raised. So what is an assertion? Basically, it's a way of crashing your program early if something bad is going to happen, right? There's a couple of examples in your textbook that are pretty good. So I'm going to go ahead and open that. Let's go ahead and see. Right. Now this is in chapter 10, which is debugging, right? Because this is actually the majority of your work, if you haven't noticed yet, for coding, which is figuring out what's going wrong with your code. So you can raise an exception, right, which creates your own errors, like this. So one way to just directly raise an error without any conditions is just by raising an error. So I'll open it up in Python over here. Right? Python. Raise exception. And you give it whatever type of exception you want over here. That's bad. Right? Exception. That's bad. Right? So raising an exception is a way to cause an error. And then you want to give a reason to the user that gives them, or to the person who's programming, some information as to why you crashed their program. Such as, I crashed because I don't like you. Right? Good information there. Right? And an example of this is like if you've got a function. So the example they use is this print box function over here, right? And this one will print a box. The goal is to print a box for the user. And if they're gonna, but basically it needs three variables. It needs a symbol, the string that's gonna print, a width, and a height. If the symbol is not equal to 1 in length, he raises an exception, right? Because he wants to only print, because this is going to be like the surrounding a box. Let me go ahead and actually open it up in the editor. Sorry. Box print. Here we go. So here's an example of this. So we ran it. The first time we ran it, we run it a bunch of times. So here we look at this for loop, by the way, for symbol with height in a tuple, right? So it's looking at basically these pairs of symbols and it's unpacking them. Star 4 4. So it printed a 4 by 4 box made of stars. Then a 20 by 5 box made of O's. Then it tries to do an X box. A 1 by 3 box made of X's. But we got an exception. It says we got an exception. What was the exception? We got a, well, So let's look at the function. If the length of the symbol is less than or equal to 1, raise an exception, right? Because we only want one symbol surrounding the box. If the width or the height are less than 2, right, it needs to have a width of at least 2 because you need 2 sides, right? So it will raise an exception then. And then otherwise it just works. So here's how the way exceptions can be used though. Notice that the program didn't actually ever crash. It used something called a try except block. So the way that works is that you have a try over here. And if it's going to fail, if you have code that you know is potentially going to fail, you put in a try block. And try blocks always are like if else's, except that you always have an optional, except the else there ain't optional. There's no Boolean there, but I'm saying that it just kind of checks. It's actually a bad comparison, but the point is that it's a 2-part comparison, unlike a for loop, which is just 1 part. It's a 2-part statement as opposed to for loop, which is 1 part. You try this, and then accept exception, right? As error. In other words, if an exception was caused, we're going to store that exception in variable error, and then we're going to handle that exception as best we can, right? And the way it handled it was by printing it. Okay. So if we and here's another example of the errors that can happen, right? Desktop, or rather, yeah, errors.py, right? If we run this, we're going to get an exception, right? This is an error message, right? We call spam, which calls bacon. And you can, what's important here is that basically a lot of the times when an error happens, I get students who tell me I don't understand what's going on. And the answer is that actually at this point you should be able to hopefully figure that out, because it tells you the error occurred in line 5 when we called spam, and spam called bacon in line 2, and then the actual exception itself was in line 4, right? So it gives you basically a breakdown of where all those of the flow chart for how the error got passed up to you. So that's very, very useful to be able to trace things. There's a module you can use to trace errors back, which is useful. But that's only really if you are getting deep into debugging those stuff. So going back to the assert keyword now, is that it's a sanity check, essentially. It's the parts where that you have, so they said it's 4 parts, I said it's 3, the assert keyword. You have the condition, a Boolean statement that evaluates the true or false. You have a comma, and then you have a string. And the reason is that basically that these things exist is because it's very common to have a logic error accidentally in your code, right? Their example on this one is like, I like this example. Say you're building a traffic light simulation. The data structure representing the stoplights and intersection is a dictionary with the keys north, south, and east, west. So and those represent stoplights that are facing north, south, and east, west. And the value of a stoplight is either green, yellow, or red, right? So, right, it makes sense that at market and second, if you're going north-south one direction, it's going to be green. And in the other direction, it's going to be red, right? You don't want them to both be red you don't want them to both be green at the same time, right? Because then you're going to get crashes, right? When you start the project, you want to write something like switch lights, and that gives you an intersection, right? And you think it's like, oh, you just simply rotate the colors, right? If we're green, we go to yellow. If we're yellow, we go to red. And if we're red, we're going to go to green. And notice that these are all if-else if statements, right? That basically, these aren't going to cascade, right? So for key in each of the stoplights. So for each stoplight, If that stoplight happens to be green, we switch it to yellow. Okay. If it's red, we happen to go to green. So this is going to look like this. So so this doesn't give you any actual errors. But if we were to call this, it's not going to crash. But the virtual cards are going to. And maybe you've written everything else, and it will take you a while to get to this error. But what the issue is that basically you should probably check that at least one of those lights is always red. So that because if one of them isn't always red, then you're going to have two people going in the same direction, right? How does that work? Yes?
Sorry for not being in the office before, but I sent an email answering back to Professor Black. So
okay.
Everything's okay. Thank
awesome.
you very much.
No problem.
Okay.
So, for instance, north-south starts out as green. It goes to yellow for the next, right? And then east-west it's red. It immediately goes to green. So you've got a yellow and a green at the same time. That's not good. That means you've got people who are if you know drivers in America, yellow just means go faster. So you've now got people who are going faster plus people who are now thinking it's okay to go. So now you've got virtual cars crossing each other. So you want to make sure that one of your lights is always red, right? So by adding this assertion statement in here, assert red that one of these is always red. Then that will help. Assertions are they're good for when you're writing it, and you can disable them by passing in the -o option when you're running Python. So that's essentially it for what I've got for you guys in terms of this. So the next thing I think we are going to do is that now that we've got actually a good grasp of Python, I think for the next week we're gonna try our hand at having some fun. And to do that, I want you guys to go ahead and install a module. Okay? So the module I want you to install is pip install Pygame. And I'm going to look over this weekend, but I think you guys might have fun trying to make some games for the last week. How does that sound to you guys, making games for the last week? Okay. So I'll come up with some kind of appropriate homework, which might just be make a game and show it to me. All right? So